Stress concentration factor calculation is an important topic in solid mechanics. Hello, I'm Armin. In this video, I will show you how to model a thin plate with a circular hole at its center. Since the plate is thin, the plane stress formulation is used. Also, because the geometry is symmetric, we only need to model 1/4 of the plate and apply symmetry boundary conditions. We will then apply the appropriate boundary load, use a parametric sweep to vary the hole diameter, and finally calculate and plot the stress concentration factor. The results will also be compared with a reference diagram. Before we begin, I'd like to briefly explain the model. When a material is subjected to a force or displacement, stress is generated due to the resulting strain and Young's modulus. The stress distribution depends on the direction of the applied load or displacement. Many specimens contain fillets and holes, and both are prone to stress concentration. This means that the stress in these regions is higher compared to areas farther away. A stress concentration factor indicates how much higher the localized stress around structural holes and fillets is compared to the average stress. There are several empirical and analytical solutions available, and the finite element method is also capable of calculating this factor. In this tutorial, the solid mechanics physics interface is used. We apply the plane stress formulation since the sheet is thin. A stationary study is selected because the problem is time invariant. This completes the model overview, and the geometry and boundary conditions will be explained in the next section. The geometry consists of a thin, finite rectangular plate with a circular hole at its center. The plate has a width of 100 millimeters and a height of 40 millimeters. Since the model has a finite length, the geometry slightly influences the stress concentration factor. However, this effect is small enough to be neglected. As shown, the geometry is symmetric about both axes, so only 1/4 of the model needs to be simulated. Two boundary conditions are applied, a symmetry condition along the symmetry axis, and an applied force on the left boundary of the model. Finally, we compare the stress concentration factor from a reference book, which will be introduced later, with the COMSOL solution. The results show good agreement. Before starting, I would like to introduce the reference for the stress concentration factor diagrams, Shigley's Mechanical Engineering Design by Richard G. Budenis and J. Keith Nisbet. Chapter 3 of this book covers load and stress analysis. That is enough explanation. Now, let's get started. I start by clicking on Model Wizard. Since the specimen is a thin sheet, it is better to model it in a two-dimensional space. In the Select Physics window, I expand Structural Mechanics and choose Solid Mechanics because I want to perform a static plane stress analysis. After that, I click on the Add button to include this physics interface. The Review Physics Interface section shows the main variables used in solid mechanics. The primary variable is displacement, while stress and strain are calculated from the displacement field and the material properties. Next, I click on Study to define the analysis type. Since this is a time-independent static analysis, I select Stationary and then click Done. Before starting the modeling process, I would like to change the length unit from meters to millimeters. Now, I want to create the geometry by defining the dimensions as parameters. I click on Parameters 1 to add the parameters. To save time, I already prepared a text file containing all parameter definitions. Therefore, I click on the Load from File icon, select the parameter text file, and click Open. All parameters are now imported successfully. The parameter D0 represents the hole diameter, H0 is the sheet height, T0 is the thickness, F indicates the applied force, and sigma is the stress formula in Pascal. Next, I will use these parameters to create the geometry. I right-click on Geometry 1 and select Rectangle. Another way is to open the Geometry ribbon and choose Rectangle from there. Now I need to define the dimensions in the size and shape section. The width of the rectangle is not important for this simulation, so I will simply set it to 100 millimeters. The height is defined using the parameter h0. Finally, I click on Build All Objects to create the geometry. Since the geometry is not fully visible, I click on Zoom Extents to get a better view. The next step is adding a circle at the center of the rectangle. I right-click on Geometry 1 and select Circle. The radius is defined as d0 divided by 2, and the circle position should be at the center of the rectangle. Therefore, I type 50 millimeters in the x direction and 20 millimeters in the y direction. Finally, I click on Build All Objects. Now, the circle is located at the center of the rectangle. In the next step, I need to subtract the circle from the rectangle. I go to the Geometry tab, expand Booleans and partitions, and select Difference. The Objects to Add field is already active, so I select the rectangle. For objects to subtract, I choose the circle. Finally, I click on Build All Objects. Everything looks correct. After creating the geometry, we can see that the model is symmetric about both the x-axis and y-axis. Therefore, we only need to model 1/4 of the geometry. I select the rectangle again and change the width to 50 millimeters, then click on Build All Objects. Next, I divide the height by 2 and again click on Build All Objects. Now, only 1/4 of the geometry remains. Using symmetry significantly reduces the computational cost and also removes the need for additional boundary conditions to fix the specimen. The next step is defining the material. I right-click on the Materials node and select Blank Material. I want to assign the mechanical properties of structural steel to the specimen. Therefore, I enter a Young's modulus of 200 gigapascals, a Poisson's ratio of 0.3, and a density of 7,800 kilograms per cubic meter. Then, I press Enter. The material properties are now defined correctly. Next, let's go to the Solid Mechanics Physics interface. In the Settings window, under 2D Approximation, we need to change plane strain to plane stress because the specimen is thin. The thickness is 2 millimeters, which is already defined by the parameter T0. Now, let's define the boundary conditions. I navigate to the Physics tab, expand Boundaries, and select Symmetry. Then, I choose the upper side and the right side of the specimen sheet. Now, it is time to apply the force on the left edge. I expand the Boundaries menu again and select Boundary Load. Then, I select the left edge of the specimen. In the Settings window, I change the load type from force per unit area to total force. The force in the x direction is equal to minus F divided by 2, because we are modeling only half of the specimen due to symmetry. The geometry is symmetric about the two symmetry lines. Therefore, the model is already fully constrained, and there is no need to add extra boundary conditions such as fixed constraint or simply supported conditions. Now, let's move to the mesh generation step. I click on the Mesh 1 node, then select Build All from the Settings panel. The mesh is slightly coarse, so I change the element size from the drop-down menu to Extra Fine. Then I click on Build All. Everything looks good. Now, let's solve the model before defining the variables for calculating the stress concentration factor. I click on the Study 1 node and select Compute from the Settings panel. The solution is complete. The computation takes about 7 seconds, and the number of degrees of freedom is 26,262. For a better view, I click on Zoom Extents to display the entire specimen. The next step is defining the variables needed to calculate the stress concentration factor. We need to determine the maximum stress around the hole and the nominal stress at the middle section of the specimen. A convenient method is to define a maximum operator for evaluating the peak stress. I right-click on the Definitions node and, under Non-Local Couplings, select Maximum. In the Settings window, I change the geometric entity level from domain to boundary. Then I select the whole boundary and the right side edge. Now the first part of the setup is complete. Next, I will use global evaluation to calculate the stress concentration factor. I right-click on the results node and add an evaluation group. Then, I right-click on the evaluation group and select global evaluation. The next step is defining the maximum stress in the x direction using the maxOP1 operator. By clicking on Add Expression, we can search for the required variables. However, the stress variables are not directly visible in this list. Therefore, I expand the stress plot, click on Surface 1, and locate the stress function name from the expression menu. I expand the solid mechanics node, then expand stress. Under stress tensor, I select the stress component in the x direction. Now I click on Plot to visualize the stress distribution. The expression field shows the exact stress function name. I copy this expression and paste it into the global evaluation. Before evaluating, I type maxOP1 in the expression field and place the stress function inside its parentheses. Finally, I click on Evaluate. As you can see, COMSOL shows that the maxOP1 operator is not available for this solution. This happens because the operator was defined after solving the model. Therefore, we need to update the solution. I go to Study 1 and click on Update Solution. Now, the operator is added to the solution. Next, I open the Global Evaluation node again and click on Evaluate. The evaluation table now shows the maximum stress around the hole and along the symmetry axis, which represents the middle section of the specimen. Now we need to divide the maximum stress by the average stress, which I already defined in the parameters. I copy the average stress expression, go back to Global Evaluation, add it as the denominator, and click on Evaluate again. The table now shows the stress concentration factor of the specimen. Now let's compare this value with the reference book results. Before that, I open parameters 1 and verify that the ratio D0 divided by H0 is equal to 0.1. Next, I open the reference figure. We can see that the stress concentration factor is approximately 2.7, while our calculated value is 2.77. The results are very close. However, we still need to perform a mesh refinement study to ensure that the solution is mesh independent. So I go back to the Mesh 1 node to view the mesh again. I right-click on Mesh 1 and select Edit Physics-Induced Sequence. Then I right-click on Free Triangular and choose Distribution. I select the quarter hole edge and set the number of elements to 15. Finally, I click on Build All. Now the mesh around the stress concentration zone is much finer. Next, I open Study 1 and click on Compute again. After the solution is complete, I return to Global Evaluation and click on Evaluate. The new concentration factor is approximately 2.74, which is closer to the reference value than the previous result. Now, let's check another geometric ratio. I open parameters 1 and change D0 to 16 millimeters. Then I update the geometry to visualize the new hole size. Next, I solve the model again. After the computation is complete, I go back to Global Evaluation and click on Evaluate. The new stress concentration factor is 2.26. Now let's compare it with the reference chart. The ratio D divided by W is equal to 0.4, and the corresponding concentration factor from the reference is approximately 2.24. As we can see, The numerical and reference results are almost identical. So far, I have calculated the stress concentration factor for 2 different cases. Now, I want to plot the stress concentration factor with respect to D divided by W. To do this, I go back to the parameters section and define a new parameter called dW. Since parameter names cannot contain a slash, I use dW instead of D divided by W. I enter an arbitrary value, for example 0.05, and press enter. This value is only temporary because it will later be replaced during the parametric sweep. Next, I define D0 in terms of dW. So, I remove the previous expression and type dW multiplied by H0, then press enter. Now, by changing dW, the whole diameter changes automatically. I'll enter 0.1 for dW and press enter. To verify this, I go to Geometry 1 and click on Build Selected. As you can see, the radius has been updated correctly, and everything looks good. Now, I'm going to add a parametric sweep. Before doing that, I'll go to Mesh 1 and click on Build Selected. As you can see, the mesh refinement around the hole looks good. Next, I right-click on Study 1 and select Parametric Sweep. In the Study settings, I click on Add and choose dW from the parameter list. I want to use a range of values, so I click on the Range button. I'll start from 0.05, use a step size of 0.05, and set the maximum value of dW to 0.8. Then I click on Add or Replace. Now everything is ready, so I simply click on Compute to solve the model. The solution is complete, and the total computation time is 57 seconds. Let's take a look at the stress concentration factor values. I click on Global Evaluation, and then press Evaluate. As you can see, only the last value is displayed. To show all the results, I go back to the evaluation group and change the dataset from Solution 1 to Parametric Solutions. Now when I click on Evaluate again, we can see the full list of values. Next, I'd like to plot these results, so I simply click on Table Graph. This plot shows the stress concentration factor versus D divided by W. We just need to make a few adjustments to the X and Y axis labels and the line thickness to improve the appearance. I think a line width of 2 looks much better. Now I want to adjust the axes, so I click on 1D Plot Group. In the Axis section, I enable Manual Axis Limits. I set the X-axis range from 0 to 0.8. And the Y-axis minimum and maximum to 2 and 3. Then, I click on the Plot button again. Now the final stress concentration factor plot has axis limits similar to those in the reference figure. Next, I'll adjust the axis labels. In the Plot Settings section, I enable the X-axis label and Y-axis label options. Then, I set the Y-axis label to KT and the X-axis label to D divided by W. Now, we have the final diagram with axis labels and limits similar to the reference figure. The tutorial ends here. Thank you for watching.